Hi there, this is Lorenz calling from the beautiful campus of the Weizmann Institute in Rehovot in Israel. Um, I'm a postdoc here and I was kindly asked to comment on a few aspects of the use of software tools for directed evolution. In my eyes, however, upfront, I have to say I'm not an expert in directed evolution, but in general, bioinformatics software tools are an integral part of these investigations in the biological sciences. And the reason for this is quite simple because, and this also applies to directed evolution, the field is very complex. So this complexity serves as a motivation to use software tools. And why is that? Well, imagine you want to evolve a certain protein from its given functionality to a novel functionality, okay? And now you might argue, okay, nature did quite well in this, so we, as humans, we are evolved and we function quite efficiently, more or less, right? But the problem is, it took quite some time. So evolution works well if you have an infinite amount of time, and if you can make many, many trials and almost as many errors. And as a researcher, of course, you don't have so much time, so you need to do this in a software assisted way. And algorithms can help us to break down complexity, to find certain substructures in data that we might focus on or might give priority to. And it can help us in a rational way to establish optimization routines and heuristics how to approach certain problems and certain cases. So I think there's no way we could intuitively come up with a set of protein modules or sequence strings or SNPs that by its combination could come up with the property of interest. So for this we need the computer, we need powerful algorithms, we need software tools. So I think the time of purely experimental labs for protein engineering is past, it's over. In the future, protein engineering will only be successful if proper software tools are used. And again, I'm not an expert in this field, so I cannot really speak from experience here. But as I understand, there's two general approaches in these software tools. One of them works prospectively, so it integrates available sequence and structural data. And the most prominent one, as I learned, is the so-called schema. It's based on a genetic algorithm where small modules of proteins, so-called schemas, which are known to interact or to function in a proper way, are recombined and shuffled, and then it is somehow scored whether functionality would be improved or something like this. And a different kind of approach is algorithms that function retrospectively. So they harness information on property data of mutant libraries. And the most prominent one here is called ProSAR, which is, in my understanding, just a statistical model of how these properties in the mutant libraries are used and recombined. But again, I mean, I cannot recommend any of these because I've not really worked with them. I just have had a quick look. But there's also some very general advice I would like to give here. I mean, in these days, there's so many tools out there. You feel a bit overwhelmed But there's no other solution than just trying these. I mean, try out the software that's out there and see whether it works for your purpose. I mean, you have specific demands. There's specific software out there. See how much you can adapt it. Try to read through the code, because this is the only way how you can understand how it works. And then try to implement it into your framework and create a more powerful software. Okay, so 1 or 2 decades back, we were in the wet lab in protein engineering, in this trial and error phase, and now at the dry lab part, we are at this trial and error. So try these tools out there, and whatever works best for you, just use it. Of course, in this line, I would also like to argue for more standard ways to benchmark software. And also in the field of protein engineering, I think some gold standard datasets would be required, where you can really test your software and see whether you always, with this very defined training dataset, always end up with the same output of your software. But iGEM as such, I mean, is the best, let's say, framework to establish these standard operating procedures for developing experimental protocols as well as software. So yes, go out there, try it, and try to standardize it and document it well. Of course, you can only use and read and understand available tools if the source code is available. So this is also a strong call for open data and open science, which is needed, because to handle this complexity, we will only be able to handle this complexity as a community, as a combined effort. This is some problem that I also know from my field of expertise. So how to constrain a parameter or a search space, a multi-dimensional, super high-dimensional parameter space. So I know this from quantitative dynamic modeling. And of course, there it's in some sense easy to constrain, because biochemical rate constants, they have a certain range. An enzyme cannot go backward, let's say. Of course, there's a reverse reaction, but it cannot go infinitely fast. So you have a certain idea about the turnover rates. And also speaking of enzymes, catalytic rates, binding rates for proteins you want to evolve, of course you can rationally constrain the search space there. But if you talk about protein modules, of course you can scrape UniProt databases and stuff. But the combinatorial explosion creates, of course, high computational demands. And the question is always, how robust is your optimization? How robust is your algorithm, your model performing? And along this line, I would rather argue to constrain the search space. So rather use a limited set of protein sequences that you shuffle and recombine. But then again, try with these standard statistical procedures to evaluate how robust your algorithms are, how reproducible they are. Because especially in the field of directed evolution, the starting point, I mean, your starting sequence is known, and you know the output, what you want to achieve, which kind of new functionality. But there are so many different paths to reach this optimum. And so rather constrain the number of paths that you can evaluate and test, and then run them several times and see whether you always walk the same way. And I think this is all I can add to this from my side. Again, do it systematically, do it thoroughly, do it openly, share it, and stay enthusiastic.